All right, good afternoon, everyone. So today we're going to finish up Unit 6, just a couple small topics, and then we'll move on to Unit 7. So the first thing to talk about in Unit 6 is to come back to this idea of convex sets. So before I told you that, convex convexity. So I said the convexity is useful because you don't have to worry about, when you're optimizing a function, if it's convex, you don't have to worry about falling into bad local minima or being attracted by saddle points and things like that. So let's talk a little bit more about what we mean by convexity. So the first thing we have to talk about is convex sets before we can talk about convex functions. And so we say that a set is convex if for any 2 points in the set and any number t between 0 and 1, this thing, which you can think of as a weighted average, or we call this a convex combination, that this thing is still in the set. So in other words, here's our 2 points. So this convex combination of those 2 points would be any point along that line segment. And if for any 2 x and y in the set, like anywhere I choose them, when I make that line segment, all the points on the line segment are still within the set, then it's convex. Here is an example of a non-convex set where we're able to find 2 points. We draw the line segment, and then we find that some of the points on the line segment are actually outside of the set, so therefore it's not a convex set. So this is what it means for a set to be convex. And then here's some examples of convex sets. Circles are convex, squares are convex, ellipses. If you're working with vectors in Rn and you consider the entire space Rn, that's convex. Or hyperplanes are convex, so if you have like a plane or a line cutting through a space and you restrict yourself to that plane or that line, that's going to be a convex set. Also half spaces, so if you have Rn and you split it with a hyperplane and you look at one side of it, that's called a half space. That thing is going to be convex as well. So these are just some examples of convex sets. So any questions on convex sets? Okay, so now we can talk about convex functions. So a function f, this is a function that's returning just a single real number. This function is convex if 2 things. Number 1, its domain is a convex set, and this second inequality holds. One way we can express this just in a few words is that here you have a convex combination on the input to the function, and here you have a convex combination on the output. Okay, so the idea is if the convex combination applied to the input to the function is less than or equal to a convex combination of the outputs, then the function is convex. So this picture here illustrates it. So here are, on the horizontal axis, we have a point x and a point y, and that means that a convex combination of x and y is any point on this line segment. Right? So that, now if I evaluate the function at that point, we would get like some of these values. On the other hand, if I look at what happens here, a convex combination of the output, that means I evaluate the function at x, I evaluate the function at y, and then I do a convex combination of those values. So here you can see that this line is always, is never below this line, or this curve. So that tells us that this curve is convex. And this has to hold for any 2 points. So, if I try it with these 2 points, it still works. If I try it with these 2 points, it still works, and so on. So that would always hold for a convex function. Now, if the function started, tailing down here, then you could imagine that it's not going to hold anymore. So you really need something like this. The function could be flat. That would be fine. Doesn't have to be strictly curved like this. But it couldn't be flat and then something like that. That wouldn't work. All right, so that's what convex functions are. And so that's the sort of property that we would like our loss function to have. Right, any questions on convex functions? How many people have seen these before? Okay, just a few people. All right, very important in engineering and a lot of other fields. Okay, so here are some examples of convex functions. Linear functions are convex. This is a scalar input here. Now, if you have a vector input, this is another way. This is how you'd have linearity in a vector input. You have some inner product plus an offset. So that's convex. If we have a quadratic function, this is convex as long as the multiplier on the squared term is non-negative. So in that case, you would have some function like this. If you made that multiplier negative, then it would be like this, and it would actually be concave. Concave is sort of if the negative of the function is convex. All right, so norms are always going to be convex, whether we're talking about the 2 norm or the 1 norm or any kind of norm. If you're wondering how to generalize this to, let's say, non-quadratics, like what if you had a cubic function or something like that? So what you need to do is you need to look at the second derivative. That needs to exist everywhere and be non-negative everywhere. If that holds, then this is convex. That would be the case for a single variable x. If you want to say what happens with multiple variables x, like this vector, then rather than looking at the second derivative, you look at the Hessian matrix, which is a matrix that contains all the individual kind of cross derivatives between all the different elements in x. And that Hessian matrix must be positive in the sense of, or non-negative in the sense of matrices, which means it needs to be positive semi-definite. Okay, so those are some ways you could check convexity. And then if you have two if f and g are both convex and you add them, the sum is convex. Or if they're both convex and f is non-decreasing, then you can compose them or cascade them and get convexity. And for us, when we've seen RSS, we've seen logistic loss, we've added L1 or L2 regularization to both. All of those things are convex. Yes?
Is the second derivative rule enough to declare a function as convex? Like, is that in its own right?
Yes. Yeah, so...
As opposed to what you're doing for bullet number 2, that's just a much more complicated expression.
Oh, sorry.
No, sorry. Like, the first bullet, sub number 2.
Oh, this?
Yeah.
I see. Yeah, this is a generic thing. So one of the troubles with this is if a function doesn't have this second derivative existing everywhere, like if I give you a function that's has a sharp corner here, that function could be convex, but you wouldn't be able to check it this way because it doesn't have that second derivative. So this is sort of like a sufficient condition, but it's not necessary.
Okay.
Yeah. All right. Okay. All right. Any questions on convex functions? We won't really be getting into a lot of details here, but I just wanted you to be aware of what they are because they are important to know when you have one or when you don't. And then we've sort of said this already, but if a function is convex and let's say that x is a local minimizer of that function, then x is actually a global minimizer of the function. So that's why we care about this. So here's just a couple pictures of a convex function. As you can see, like as you can see, like this has a unique minimum in this case. Unique, yeah, minimum. This one, which is non-convex, you can see it has two local minima, and then this local minimum is the global one, and this one is a bad local minimum. It's has a height that's strictly above the global one. It is possible you could have a function that's convex where you have many minima that are all equally good, but they're all global minima in that case. This is sort of the situation we'd really like to avoid, is when there's a bad one, gradient descent would get trapped in here, but gradient descent would not get trapped in any bad spots here. Okay, so that's really all I want to say about convexity. Any questions about anything with convexity? All right. Okay, the second thing I want to talk about just briefly, because we're going to be using it in the next unit, is constraint optimization. So until now, we haven't really talked about constraints. When we want to optimize a function, let's say over a parameter vector w, we just allow w to take on any values, and there's no constraints on them. But in some applications, you do find that you want to place constraints on things. So like, just as one example, if you have a probability mass function and you wanted to optimize over all probability mass functions, you have to make sure that all the elements sum to 1. That would be an example of an equality constraint. And you have to make sure that all the elements are non-negative. That would be the example of an inequality constraint. And here, when we're writing an equality constraint, here we actually have capital L different equality constraints. Each one, let's say the little lth one, we're writing this way. We can always write it with equals 0 here, because even if the original constraint had a non-zero value like 1, what I could do is I could move the 1 to the other side and redefine the function so that the constraint gives you 0. So without loss of generality, you can always have equals 0 here. Similarly, with the inequality constraints, you can always write them as the mth inequality constraint is less than or equal to 0. Okay, so you might be trying to minimize a function under certain equality constraints, one or more, and possibly inequality constraints. So these come up a lot. So, okay, so there's the basic method that people use to handle this situation is you reformulate the constrained problem as an unconstrained problem that has additional design variables. Okay, so let's say that this is the original problem like this. So we have some cost j. We want to find the minimizer of it. And in addition to minimizing this, we also have to make sure that our equality constraints are obeyed and our inequality constraints are obeyed. So that would maybe be how we first write the optimization problem. But then what we're going to do, let's just first talk about what happens with equality constraints. If we have only those, then what we do is we add some new variables to our problem that we call Lagrange multipliers. And if I have L equality constraints, I'm going to add L of these new variables. And I'm going to define a new cost function that is my old one, j of w, plus a new term that looks like this. Here's my new variables, lambda L, and here are my linear constraints, or my equality constraints. So this is a new cost function that involves both w and lambda. Lambda is the vector of all those Lagrange multipliers. And now it's enough to minimize this new cost over both w and lambda. And what's nice now is there's no constraints at all. So you can attack this with the methods, common methods. So for example, if this function is differentiable with respect to both w and lambda, then we can use the method that we use a lot, which is just to take the derivatives with respect, or the gradients with respect to w and lambda, and set them both equal to 0. So that's nice. You start with this difficult constraint problem, and then you just rewrite the cost function in a way that allows you to solve it with standard methods. Okay. Yes?
Wouldn't there be like the trivial solution of lambda equals 0? Because then you don't have any of those additional costs, and it's just the cost of j omega. So like, is that?
So, yeah, so the key thing to remember is that there's going to be an optimal lambda. Because when you do this minimization, you're jointly minimizing over W and lambda. So lambda, the optimal lambda is probably not going to be 0. It might be. And if it is 0, that just means that you didn't have to enforce the constraint, where the minima was. Like the constraint wasn't really involved at all. So that can happen, but you wouldn't, by solving this problem, you're going to find the optimal lambda. And let me try to explain now why this works. So as we know, if you indeed find the minimizer over both W and lambda, then you know that the partial derivatives with respect to each of those individual lambdas evaluated at the optimal solutions for those vectors. Let's see what happens. So take the partial derivative of this with respect to lambda L. What do you get? It's the partial derivative with respect to lambda L. Just HL, right? So I know that this has to equal 0, which means, as you can see, that HL must equal 0, and that's exactly the constraint we're trying to enforce. So that kind of explains why this works. You set up this cost so that by finding these minimizers, the optimal lambda, you automatically enforce the constraints that you need to enforce. Okay, so hopefully that explains why you add exactly that term and why this works. All right, any questions on that? Okay, so it turns out, I'm not going to get into the details because there's a lot more details when you involve inequality constraints. But at a high level, the process is very similar. You have, here's the same term you added before, and now you add another term that has some variables mu, and these are your inequality constraints. And now you have 3 sets of variables, and you want to do an optimization over all of those. But there ends up being a few more rules about what has to happen with those mu variables. If you're curious to know more, the most recent version of the slides that I just uploaded this afternoon have a link here to a wiki page that describes stuff. It has to do, it's called the KKT conditions. It's kind of mathematically a bit intense, but if you're curious to know more, you can learn about them. Or you can take any one of a number of optimization courses we have at OSU that get into these topics. So I'll give a list of those in just a moment. But those are really the things. Just obviously I haven't talked much about this, but I just wanted to talk a little bit about it because we will see these problems arise in the next unit, and just so you have a little bit of background and it makes sense, why you would attack things that way. All right. Okay. Any other questions on constraint optimization? Okay. So and there's definitely a lot of other things we did not talk about. So one kind of well-known class of methods that's taking gradient descent a step further. You can think about it as using a matrix-valued step size instead of a scalar step size. Using a Hessian matrix in addition to a gradient, that would be Newton's method, and there's some faster versions called quasi-Newton's methods. These methods are like gradient descent, but they converge in many fewer steps, but the steps are much more expensive. And if you have a perfectly quadratic cost function, Newton's method will jump to the solution in one step directly. Now, in practice, you usually don't have a totally quadratic cost function, so it's going to get there quicker than gradient descent, but every step will be more complicated. So that's an important topic. Another important topic, especially for us, is what to do when your cost function is not differentiable, like in the case of lasso with this L1 norm. The gradient does not exist everywhere, so how do you attack it? You can't just use gradients. There's a whole different class of methods that you can use in that case, where the gradient is sort of replaced by this thing called the proximal operator. So that's an important topic if you want to get into those details. Another comment is that the Armijo-based optimizer that we use works really well with convex functions, but with non-convex functions, it's not necessarily going to work well. In fact, what it might really try to do is converge right into the local minima that you started it closest to. But actually, in deep learning, you might want to jump out of this bad local minima and into a deeper, better one. And so for that, we'll talk more about some different methods that can help with that. So anyway, here's a list of some optimization courses that we teach here that are useful if you want to learn more about this stuff. So there's 5500, which is taught every autumn. It used to be called 5759. Or if you want to learn specifically about convex optimization, there's this course 6500, spring, odd years. So I think it's being taught right now. And then there's a more advanced course called non-convex optimization for machine learning. It really is very machine learning specific and has some really cutting edge techniques. 8101, that is taught, I think the original idea was to teach it spring even years, but I think it's going to be taught autumn, maybe autumn odd years, or no, autumn even years, I think. So we're still trying to figure out the offering schedule for this course. Okay, so that's really all we have in Unit 6. Are there any last questions about anything? Okay, great. So let's jump to Unit 7. So Unit 7 is, again, going to be about classification. It's going to get into a more advanced method called the support vector machine. And all right, so maybe let's get into it. So the motivating, the demo and sort of motivating problem is digit classification. This is one of the most popular data sets in machine learning. It's called the MNIST digit data set. And so this was created back in the 80s with the goal of being able to have an automatic mail reader, envelope reader, so that, because at that time, people in the post office had to look at every envelope and try to figure out what was there, and they thought, well, maybe we can build a method that will automatically, a computer method that will be able to recognize digits, like zip code digits. And so what they did is they had many people write zeros and ones and twos. They collected 70,000 examples of them. Each one of these is a 28 by 28 grayscale, in other words, black and white image. These are examples of some of them, as you can see, zeros, ones through nines. And the reason why this is popular for machine learning is it's nice in the sense that it's not too simple, it's not too complex. So 70,000 examples is definitely a lot, but it's not nearly as many as some other machine learning databases. And these images are relatively small, 28 by 28, so that all that helps, like in terms of training time. You can train models on this, just on your own hardware without having to have access to some massive server farm or something. So it's simple, it's widely accessible. There's a lot of people have worked on it, so there's a lot of benchmarks. It's built into, well, it's easy to get. You can get it with OpenML. And when you print out the shape, here you can see that download the data set. It's 70,000 examples, and 784 is 28 by 28. So each one of these images has 784 pixels. And as we'll see, you can think of them as an image or as a vector, either one. So in this unit, as I said before, we're going to focus on something called the support vector machine. So this is not a state-of-the-art model by today's standards, but it's historically, I think probably at one point it was state-of-the-art, and it's quite good. So here's a table from a Wikipedia page on MNIST that shows just a number of methods and error rates. And here you can see like the best method is among these. I'm sure there's other ones out there, but convolutional neural network that's getting 0.17% error rate. So 17 errors in 1,000, which is pretty good. And when you go down to the support vector machine, you see that it's 0.56. So it's not state of the art, but it's pretty good, right? It's not bad. When you look at some of these other ones like linear classifier, it's like 7.8%. So it's an order of magnitude worse. So anyway, that's kind of a motivation. So let's talk for a little bit now about how we work with images in Python and in NumPy. So it's typical when you work with grayscale images that the pixels are 8-bit numbers. So they're integers between 0 and 255. So 0 is the darkest color black, 255 is the whitest white. And here's just an example image of a 7. As I mentioned, there's 28 pixels in either direction. And so for visualization, obviously we want to think of this as a matrix, print it out as a matrix. But in working with it, just with a regression code, rather than working with it as a matrix, often we just rasterize it or we vectorize it into just a long string. In this case, it's going to have 784 values. So when you do this, you clearly lose the structure. There's sort of a two-dimensional neighborhood structure here, which is lost once you go down to 1D. But you still hope that the algorithm or whatever is going to be smart enough to figure out the patterns that it sees in these vectors to do the classification. In any case, you're clearly not losing any information. You can get back the original image. So it's just a matter of convenience because so far, like all the methods we develop, like logistic regression, works on vectors of features, right? Not matrices of features. So if we vectorize it, we can just use all the stuff we've developed so far. So in NumPy, there's different ways to do this. One command is .ravel. That will, I think it should have been called unravel because it's sort of like you're making this thing into a long string. But and if you want to go the other way, you can use reshape. This way it's very clear. Just no matter what size this is, just turn it into a vector. But when you're coming back the other way, you have to tell it exactly what size of a matrix you want it to be turned into. And so there's another comment about some of the details here. When you look in papers and books, this notion of vectorization is a pretty common thing. So if you're given a matrix and you want to vectorize it, so maybe in a book it would be written like vec of x. The assumption there is that you're going to do this vectorization column-wise. So you'll take the first column, that will give you the first 28 entries here, and then you'll take the next column, and those will give you the next entries and so on, and then these will be the very last entries. Right, so it's taken column-wise. We try to enforce that. Okay, and that's the way that I will be writing like all the homeworks and exams and everything. Well, whenever you see vectorization, that means do it column-wise, just to be consistent with how all the rest of the literature is done. But now when you try this in NumPy, it actually works on rows. So if you vectorize this matrix, what it would do is it would make a vector where that would be the first few elements, and then that would be the next few elements, and so on. So you just have to be aware of this. The simple fix, if you want NumPy to work consistently with book notation, is you just transpose the matrix before you vectorize it. And then if I transpose this, then this will be the first row, second row, and so on. Okay, so that's just a minor thing, but important to know about.
Each value in that vector is between the 0 and 255?
So when we work with images in the standard framework, or standard grayscale images, yeah, the pixel values will be integers between 0 and 255. Now, if you started to do some processing, you might find that you get floating point numbers. But usually they're stored as 8-bit integers just because that's much more efficient than floating point might be like, 16, 32, 64 bits or something. So when they come in a data set, they're typically 8-bit integers. And this is the most common format for black and white images. As we'll talk about later in Unit 9, once you deal with color images, you actually have like red, green, blue. So you have like one of these pictures for the red channel, one green, one blue. And so you have like, 3 different images, maybe each one will be 0 to 255. But for black and white, this is what we do. Okay. All right. Any other questions? Okay. So commonly we want to plot things. So here's a little bit of code to plot things. So here we made this plot digit code. The main command we're using here is plt.imshow. So plt is your standard matplotlib library that we've been using a lot, and imshow is just the image show command. And we're doing a few other things like turning off the X and Y ticks so that you don't have little ticks because they're not really needed for an image. And this function starts with a vector and then reshapes it to 28 by 28 in order to plot it. And that's just because, as I said before, we tend to work with vectors until we plot things. We're working with 784 dimensional vectors. So, and this is just a little bit of pre-processing. So when we download that MNIST structure, if you want to get out all the images, you would do mnist.data. And this is going to be a 70,000 by 784 matrix. And then you also need to know the label. Like you need to know that this is a 7, this is a 3, this is an 8. And so the label data is in mnist.target. I can't remember what format it's in originally, but here we're reformatting it as an 8-bit integer. I don't remember exactly what it comes in originally, but that's what we're doing here. We're saying make those labels 8-bit integers. And then this code just shows like, let's select 4 random digits. So here we're using NumPy random permutation. That what it's doing is, okay, so first we're getting number of samples. We're taking our X matrix, and we're looking at how many rows it has. So as we said, this is going to be 70,000. And then this next thing here is taking the list of numbers, integers from 1 to 70,000, doing a random permutation of it. And then what we're going to do is we're going to just look at the first 4 entries in that random permutation, and that will pull out 4 random images from our database, and we're just going to plot them using this plot digit function that we created above. And that's what plotted. And every time you run this, it will give you 4 different digits. And as you can see, like most of them are pretty easy to classify as a human. Some of them are a little challenging, but most of them are pretty easy. Okay, all right. So since we learned about multinomial logistic regression in Unit 5, that's the first natural thing to do is to try it. To make the training process a little faster, rather than using, so I think the typical train test split for MNIST is 50,000 training, 20,000 test, but rather than using that, we're just going to use 10,000 for training and test to make things go faster. We could do a little better if we use more, but this is good enough for now. And so here's where we split our data into training and test. And here's another thing that's often important to do. So notice that we're taking the original features, pixels, we're dividing by 255, right? Now that's going to scale them from 0 to 1. We're multiplying them by 2, so now they're scaled from 0 to 2, and subtracting 1, so now they're scaled from -1 to 1. And that -1 to 1 is going to work a lot better with various algorithms and so on. Sometimes you get into weird effects if all your pixels are positive and you work with them. So this is basically just a way of centering them. and you're scaling them all the same way, and you're just moving them from 0 to 255 to the range -1 to 1. Okay. Another kind of important thing that's is notice that there's a .0 here. So what that does is it means this is a floating point number, and it means that the result of this division will be a floating point number. If you're not careful and you leave this out, you have, I can't remember exactly what happens, but there's cases where you can get into trouble when you do like integer and integer divisions. It quantizes things in strange ways, and you don't get what you think you're going to get. So in NumPy, it's important to distinguish integers like 255 from floating point numbers like 255.0. Okay. Yeah, so there's a little note here. This thing will actually fail. X divided by 255. What am I saying there? Oh, okay. Yeah, so there's another little interesting thing. If you move this multiplication by 2 to the front, that actually causes problems as well, because I think what happens is this 2 times x will be an integer. I can't remember exactly what happens, but the order of operations basically matter.
It would just overflow.
Yeah, that's what it is, I think. Something, yes, that's right, because if x is 255 and you multiply by 2, then it wraps around and goes crazy. So sometimes like little things like this, you got to be a little bit careful how you do it. Okay, so anyway, we have our training and test data. We select a pretty fast solver, LBFGS, and we run linear or logistic regression. We're going to use multinomial because that tends to work better than the one versus rest. We're going to use a pretty small value of the weight that is on the L2 regularization, run it for 500 iterations, and let's see what happens. The accuracy we get is 90%. So if you remember that table from the beginning, that's definitely not awesome. It's maybe not terrible, but 10% of the time we're making an error. And if you look at some of the errors, like this one, the true digit was 1, but MLR estimated that this was a 1. It thought that this 4 was an 8, thought that this 9 was a 3, thought that this 3 was a 5, and so on. You can see it's not doing perfectly. So our question here is like, can we change our approach a little bit? Can we kind of understand what is going wrong with MLR and then fix it with a new method that is going to be our support vector stuff? So that's our motivation. So to understand that a little bit better, let's kind of think about MLR, multinomial logistic regression, again, and just sort of summarize it to refresh our minds. So this is what happens when we want to classify a test vector X, so that's our test vector, which is in this case an MNIST image. This is what we do. We look at our different class hypotheses. So what is K in this case? Capital K. How many classes do we have? 0 through 9, so 10. Yeah, we have 10 different classes. So for each class, 0, 1, 2, 3, this is what we do. We design this weight, BK, and this vector, WK, that classify X as either in class K or not in class K, right? That's the approach we use. This is the so-called one versus rest approach. And then once we have all those parameters designed, at test time, we compute a linear score, which we can call ZK, for each of these K. This way, we take our bias and we add to it the inner product of X and WK. And remember that this score is a real number. So what does it mean? Do you guys remember what it means if the score for one particular K is very large? What does that mean qualitatively?
High probability?
Yeah, it means that we believe that the probability of that class K being the true class is high. And when the score is very small, which could be like all the way, you know, very negative number, that would be very low probability. And so so that's basically, that's what these scores mean. Another way we can think of this is through the probabilistic model that we used for logistic regression. So this is the probability of X being in class K. According to the MLR model, we use the softmax. This is exactly how you go from the Z's to the probability, is through the softmax. The softmax, you can think about it as a way to map vectors, or sorry, yeah, way to map a vector of these Z values. So put all these Z values together. It maps that to a probability mass function. That's one way to think about what the softmax is doing. But in any case, remember our goal for classification, we don't really care about what these probabilities are. We just want to know which class for this sample is the most probable, right? That's all we care about. So we're just maximizing those probabilities over K, which means maximizing the softmax things over K. But for that, all we need to do is find the K that makes Z the largest. That's really all we need at the end of the day. This whole softmax thing was very important when you train the weight and bias. But once you're done training, you don't have to use the softmax for classification. You just compute your scores, you know, all capital K of them, and you just look for the largest one. And that's the one which you believe is the most probable for that X. Okay, so here's a visualization of the whole process. We start with a test sample, convert this to a vector, rasterize it. We make this weight matrix where each row is one of these WK vectors. So the first one are the weights for class 1, second row is weights for class 2, and so on. And then we stack the bias coefficients into this B vector. And we do this matrix vector multiply, B vector plus W transpose X. That gives us the vector of scores Z. If you want, you can map this vector of scores to probabilities using the softmax. You don't need to. It's enough to just look through this vector and find the value that's the largest. And that's what you say, I believe sample X is in that class. Okay, so that's sort of just a review of the procedure. Any questions on this? Okay. So in order to visualize what's going on, let's think about it this way. If X really is in class K, we want that the score ZK is really large, right? We want it to be the largest, and we just want it to be large. And so how do you get a large score ZK? It's really all about this term. You want that this weight vector is somehow, for any X in class K, you want that this weight vector causes ZK to be large, right? And so how, if that's your goal, how could you create a weight vector such that for any X from class K, this thing is large? You just make it, you make the weight vector itself look like an image from class K. Because then the inner product is maximized, right? When they match, they're pointing in the same direction. So that's essentially what happens. So, so what we can do to figure out whether, you know, how is MLR working, we can look at the weight vectors that it learned, but let's actually not visualize them as a vector, let's reshape them into a matrix and look at them that way. So here's for classes 0 through 4, just because I don't have space to plot all 10, but so this is what the weight vector looks like for class 0 if we only used 100 training samples. And as you look at it, it really does look more or less like a 0, right? So gray, this gray color, that would be value 0. The white color is large values, positive values, and the black color is negative values. Okay, so this weight vector that it learned for class 0 actually does look more or less like a 0. And the one we learned for class 1 really does look like a 1. The one we learned for class 2 looks like a 2, 3, 4, and so on, right? This is what happens when you use 100 training samples. What's kind of strange is when you use our 10,000 training samples, and now you look at the weight vectors, they look kind of crazy, right? You can't really, it's hard to see the 0 in here. It's hard to see that there's a 1 in here, or a 2 in here, 3, and 4. It just looks like somehow the method learned to focus very much on single pixel values. You know, it's like, oh, I noticed over these 10,000 samples that all of the 1s have a bright pixel here, and they all have a dark pixel here. But that's kind of weird almost, right? It's, in some sense, it's almost like overfitting to the training set. It's really focusing on these strange details that probably have more to do with the particular 10,000 samples that we used, rather than like something structural about 1s or 2s and so on. And what's particularly interesting is that this change happened as we went from using just a few samples to many. With a few samples, things were working more like what we would expect intuitively, and then with a lot of samples, we seem to be seeing some strange behavior that, you know, might result in overfitting. And I don't want to give you the impression that somehow this classifier learned from 100 works better than this one for 10,000. No, this one really does work better than this. But it's just that, you know, when we look at these, we can maybe get an idea that, okay, somehow multinomial logistic regression is really focusing on a bunch of kind of weird details that are maybe not that important to this classification problem. So is there another strategy that we can use that that's going to work maybe better? And the other strategy, just in words, is like this. Rather than using all 10,000 samples, why don't I find a few important samples that are really hard to classify, and then I'll just train my classifier from only those, and I'll throw out all the other ones and say they're not really helping me. They're just distracting me. Let's just find a few important ones and build our classifier based on that. That is the idea behind the support vector classifier and all the stuff in this unit, is figuring out which samples you should focus on, not just kind of using them all equally. So that's sort of the idea. Any questions on what we see here? Yeah.
This is more of a curiosity, but like the edges of the backgrounds are all like that very uniform gray. Is
Yeah.
that actually part of the 28 by 28, or is that like a background you put on?
No, it is. It's just because when you look at the images themselves, there's almost no important information in the outer pixels. Right? So like for all the images, it's probably black along the edge. So the classifier learned basically to ignore that. Yeah, so that's why this is like a 0 value, that color gray. You know, so once in a while there's a few that near the edge are non-zero, but yeah, mostly it's just ignoring those. Yeah.
These overfitted samples of WK, so by us are not recognized, but are they recognized by the score that they are similar to X, but the score is maximized for these?
Well, so in the end, it gives us 90% accuracy. So they are working to a certain extent, not state of the art, as we know, but yeah, they're doing reasonably well. It's just we're trying to improve it. We're trying to figure out, like, is there some sort of new idea we can attack the problem with that's a little different than logistic regression that will do a little bit better.
So overfitting here is not as bad as like increasing the model order before and now like very bad overfitting. Right?
Yeah, I guess it's not overfitting. This is not a. We don't really have a model order selection. Well, I don't know. Yeah, we don't have like as direct of a model order selection problem as we did in polynomial regression. But the general concept, when you start to see that your classifier is focusing on some weird randomness in your training data rather than structural things, that's the idea behind overfitting. So that's just kind of qualitatively how I would describe what we see happening here. Seems to be overfitting. It seems to be finding some patterns in the data that, as a human, I'm surprised that it's focusing on that. Yeah, but that's what it's doing, and it's working okay. Maybe we can improve it. Right. Okay, good. So any other questions on this stuff? All right. So, so to kind of figure out this new idea, which has to do with focusing on the training samples that are the most challenging and using only them, we have to come back to the very beginning, and we want to kind of understand the geometry of our decision boundary and what's happening when we create that boundary in our data space. So here's a sort of just, it's a contrived figure, but it shows a number of sort of important things. So, okay, first of all, what we're showing here is we have some red data points, and red might be, I don't know, it doesn't really matter, but maybe red is y equals 1. And then for blue, that would be y equals either 0 or minus 1. We use them interchangeably. Sometimes the math works out easier for one or the other, but conceptually we can think about it as like either y is 1 or y is not 1. Okay. But as you can see with this particular data set, this is an easy one because it's possible to come up with a decision boundary where you perfectly classify all your training data, right? All the blue points are on this side of the line. All the red points are on this side. So we're happy. Seems like, at least as far as the training data goes, things are good. But what can happen with test data? Is it necessarily going to be perfect? No, right? Because test data, maybe we'll have a red test point that's over here, we would make an error. We don't know. And intuitively, like the closer our training points are to this line, that makes us a little bit nervous that we might have some test points that are that close or even closer, maybe even on the wrong side, right? So by learning about, by maybe focusing on the training points that are closest to the line, maybe that would be a more robust way to design a classifier than getting distracted by these ones, which are very easy to classify. So that's sort of the idea behind the methods in this section. Okay, but there's a few important things just mathematically that we need to understand in order to go forward. And so the first thing is that this boundary has a nice mathematical expression. And this comes from remembering that when you're right on the decision boundary, that's the place of most uncertainty, right? If a sample is right on the boundary, you just don't know how to classify it. It could be one or not one. You have no idea. So that's the point of maximum uncertainty. And in terms of the score function, in binary classification, that's what we assign to 0. Score of 0 is the worst. If the score is positive, you'd be more confident it's one class. If it's negative, the other. But when it's 0, you have no idea. Okay. So in order to figure out which x's, so x are our features, which x's give a score of 0, it's just simply this equation here, or this set. So remember that this is the equation for z. Z is the bias plus the inner product between the features and the weight vector. So if you're saying this set of points is what I'm interested in, how do I describe that? Mathematically, it's just the set of x such that this equation holds. Right? And that's going to give you all these x will satisfy this equation. Okay. And we call this a hyperplane because although in this picture it's just a line because we're working in 2 dimensions, if we were working in 3 dimensions, it could be a plane. If we're working in 4 dimensions, it's a 3-dimensional object, right? So it's always something of dimension less than the ambient space, and we call that a hyperplane. Okay? So the first important thing to notice is that this hyperplane is orthogonal to the weight vector. So here, I've plotted the weight vector. Here's a hyperplane. As you can see, there's a right angle there. Okay, so why is that? Why does that happen? Well, we can do a very short little proof. So for any 2 points on the hyperplane, and they can be really any ones as long as they're different from each other, we know that this equation holds, right? This is just the equation that holds for any point on the hyperplane. So let's just write out those two equations separately. So we have b plus x1 transpose w equals 0, and we have b plus x2 transpose w equals 0. And let's just subtract them, subtract one from the other on both sides, and you get x1 minus x2 quantity transpose w equals 0, right? You get this equation here. And hopefully you remember that when you have two vectors that give you an inner product of 0 or dot product of 0, that's the definition of orthogonality. These two vectors are orthogonal. And so w is one of the vectors, right? The other two vectors, this is going to be the line connecting them. And so that line is always going to be pointing, it's always going to be like collinear with my boundary. And if you want to reference that line to the origin, you can move it here, and you get that orthogonality here, or you can see the orthogonality here too. So this is the first point. A hyperplane is orthogonal to W. Okay. So we're out of time for today, but we're going to learn a few other important things from this picture, and then we'll eventually put them together next time to get the simplest version of our method. All right. So we'll see you guys on Friday.